What a wonderful number of people in this room, which makes my heart beat as a geology lover. It's good to know that so many of you are keen to know more about our local geology. And we are very, very glad to welcome Alan to talk to us about the volcanic history of the region or the area. Alan's spoken to us about several geological features in our area, and we know just how much knowledge he has and how much detail he goes into. So we're looking forward to a very interesting session. Over to you, Alan.
Thanks, Jo. Well, good morning. Can everybody hear me? Great. What I propose to go through in this talk this morning, I'll first of all give you a worldwide coverage of how and why volcanoes occur, to give you a bit of a background when we talk about the local situation. And then I'll talk about some of the local volcanic eruptions in our local area. And when I say local area, I'm going to take examples from Rocky Cape in the west, through to Sulphur Creek in the east, and down to Yolla. So it's a fairly confined area that I'm going to look at. But of course, I'll be drawing on information from a further afield to explain what's happened locally. Now, the volcano shown on the screen at the moment is in Iceland, and it's probably the closest sort of example that I could get to what eruptions have occurred close to Wynyard. Going the wrong way. When we think of volcanic eruptions close to Wynyard, Table Cape comes to mind immediately, and in this photo you can see the red soils on the top of the Table Cape and then stretching off towards Boat Harbour. Most of that material would have erupted out of Table Cape, but there are some vents further to the west close to Boat Harbour itself. Now, Table Cape is an interesting volcanic feature because it's brought to the surface some rocks from the mantle, and these are called xenoliths, and it's given us some information of what's happening in the mantle below Table Cape. And it's also allowed geochemists to work out how deep the crust is below Table Cape. Table Cape was named by George Bass and Matthew Flinders when they came through on their exploration voyage to find that Tasmania was separate from the mainland. And this little plaque is in the park opposite the Bushrangers Hotel. Another feature that you would be familiar with close to Wynyard, Doctor's Rocks. Now, Doctor's Rocks has formed by a different process to Table Cape, even though they're both volcanic. And I'll go through the processes in a few moments of how these features formed, but Doctor's Rocks has formed partly by Tasmania rifting apart, and also by the passage of hotspots underneath. Now, Table Cape is formed solely by a hotspot, and I'll talk about these terms in a minute or two. Now, if we look at a world map which shows all the volcanoes worldwide, you'll notice that around the edges of the Pacific Plate, there is almost a continuous line of volcanoes. And these are due to the movement of the tectonic plates, which I'll explain in the next slide. If we look at Iceland, Iceland is right on a ridge through the Atlantic Ocean, and it's the only place in the world where volcanoes form due to spreading of the sea. Another feature that I'll point out is a line of volcanoes through the eastern part of Africa, and this is due to the fact that Africa is starting to split apart at that along that line. And then we have other features like these ones here, which are due to hotspot activity in the middle of the ocean. And you'll see there are a little line of volcanoes running back from that. And you might be able to pick out a feature running up through there, which I'll show you in a moment or two. Now, on the table out the front here, I've got two examples of volcanic rocks. The black one is taken from the cutting through Doctor's Rocks where the Bass Highway runs, and the white one possibly comes from one of these little islands down here. I picked it up on the southern end of King Island, and it actually floated across from that point. Now, if I've got a tub of water here, I can put that in there and the rock actually floats. So there's quite a variation in volcanic rocks, and that's probably almost the extremes you'd get. One's white, one's black, one floats, the other one would sink. Now this is a diagram of the tectonic plates that make up the world, and all these plates are continually moving. Now, on the previous slide, you would have noticed that there were volcanoes all around the Pacific Ocean, and they match up with these dark blue toothed features running around here in South America as well. And what's happening there is that one tectonic plate is sliding down underneath another one, and that's where we tend to get some fairly explosive volcanoes. The lighter blue lines, which run through the central parts of the major oceans, are where we get volcanic activity that is making new plate material. So we get, in the case of the Indo-Australian plate, this feature here is making new plate, and it's pushing the Australian landmass northwards at around about 70 millimetres a year. And I mentioned Iceland before. You'll see it's right on that blue line. So the volcanoes that we see in Iceland are actually part of the process of making new tectonic plates. Now, the other colour that's shown is this colour here. That's a transform boundary where plates are sliding past each other. Now, you may be familiar with the New Zealand situation. The Southern Alps in New Zealand are due to that sliding motion pushing up the mountains. Now, this is a diagram that illustrates the formation of the mid-ocean ridge, which is this feature here, where new plate material is continually being made because you've got rising magma coming up through the gap in the oceanic plates, and one plate gets pushed one way and one gets pushed the other. Then when the oceanic plate gets close to a continental plate, the continental plate tends to be less dense than the oceanic plate. So the oceanic plate gets pushed down, and it gets pushed down to a point where partial melting occurs. Now this is happens because it gets hotter further down, and also because this plate is saturated with water. There's a fluxing mechanism here that allows the melting to occur at slightly lower pressure or slightly lower temperature. And the rising magma comes up and you get volcanoes in this area here. Now, this is an example of the differences in polarity of the magnetics of the rocks that are being formed. When a rock is molten, the magnetic particles in it, little particles of magnetite generally, align with the magnetic poles of the Earth. And when the poles flip the other way, so do the little magnetic particles in the molten rock. So you get a series of stripes. That's the mid-ocean ridge, and either side of it you get these bands of different polarity. And these were discovered just after the Second World War, when they were starting to do surveys to help with the navigation of submarines. And these can be dated, and the further away from the mid-ocean ridge, the older the rock is. And that's shown on this diagram on the right. You may not be able to see those figures very well, but that's the youngest at the top, and this is the oldest down the bottom. And so there's the mid-ocean ridge, younger rock here, older rock further out. Now this is a North American situation. That's Vancouver Island there. This is a volcano that erupted due to the ridge that we were just looking at, Mount St Helens in 1980. Very explosive eruption. And there was a United States Geological Service observer up on the mountain just before it erupted. He was able to get out a little message, "This is it," and he was gone. So there was quite a lot of destruction from that volcano, and downwind there was acid rain due to the cloud of volcanic ash. This is the situation of the mountain. That's Mount St Helens there, and you'll see it on this map in relation to Seattle. You'll notice that Mount St Helens is a little bit further west of the other mountains. And when we look at a cross-section, you'll see that the magma has formed slightly further higher up than the ones that are further to the east. And it's likely that there was a higher content of water or other volatiles in that magma, and that's why the mountain was so explosive when it blew off. So that's what we call a subduction. This is the mountain after it had been erupted, and you notice the great hole in the mountain. Very explosive situation. Now we'll move to a different type of volcanic eruption. In this case, there are lines there that show where the eastern part of Africa is starting to rift away from the rest of Africa. And this type of eruption is probably in some ways similar to what's happening at the mid-ocean ridges, but the volcanoes are somewhat different This closes in a little bit on the situation. You can see the lakes in between the black dashed lines. That's where rifting is occurring, and the lakes form in the low valleys where the crust gets much thinner. The red triangles mark where there are volcanoes, and the yellow arrows indicate the directions that the crust is moving away from those rifting zones. Now we'll have a look at this particular volcano here. That's it erupting, and you'll notice that the ash cloud above the volcano is somewhat more subdued than the ones that we saw over Mount St Helens. Now, it had an eruption that was very much lower temperature. You'll notice the temperature there, 540 to 590. And it had a very fluid lava due to the fact that the lava contained a lot of carbonates, mainly things like anchorite, a little bit of calcite. So a very fluid lava just ran down the side of the mountain, and this is due to differences within the mantle of the earth. It's not all the same material that gets erupted. In the same area, we've got the world's largest intact caldera. Now, this is a formation that occurs when a magma chamber empties almost completely, or at least partially, so that there's a big cavity below the ground. And the roof of the cavity is unsupported, and it just drops into what was the magma chamber. Now this is 260 square kilometres in area, so you're looking at something like 18-20 kilometres across. So a roof of that size is obviously unsupportable. This is now a World Heritage Site because of the fact that it's a huge example of that type of formation. Now the next type of eruption that I'm going to mention is the hotspot. Now you can see a line of volcanoes and then another line there. This point here is a bend in the line, and that was due to the fact that the Pacific plate changed direction. The tectonic plates are all rubbing against each other and jostling each other, so we do get changes in the movement. And you'll notice that that's where eruptions are occurring at the moment, and the ages of the volcanoes get older, and something more than 81 million years old up there. So the hotspot has been continually erupting for that length of time. Now the reason that we've got lines of volcanoes is the fact that the hotspot stays relatively fixed, and the tectonic plate moves over the top of it. So originally the tectonic plate had a direction of movement here, and then it changed, so it's now running in that direction. Now hotspots can be oceanic, and they can also be continental. This is another view of the same hotspot chain, just close up to where it's now erupting, and there's the rest of it. We don't really know why hotspots occur or why they can stay fixed for so long in one spot, but they work. We've also got hotspot chains close to Australia. Fraser Island there, Sydney, and this is a chain offshore running down to Lord Howe Island. Now, Lord Howe Island is, you can see there, the shape of a volcano with a probable crater in this area, and also Ball's Pyramid close by, another volcanic feature from the same hotspot chain. They happen on land as well. This is the Tweed volcano, Mount Warning shown there, looking from the west. That's the first point in Australia that gets a sunrise. And this is a huge volcano that was due to a hotspot activity. Now, these are some chains of hotspots that occur on the Australian mainland. That's probably the longest hotspot chain on land in the world. And then the one that we were just looking at, running from Fraser Island down to the Combourne Plateau with the Tweed volcano in it, is this one here. And a little bit more detail of the top part of this hotspot chain, which is known as the Cosgrove hotspot chain, because the last volcano, Cosgrove, is down here in Victoria. Now, the next type of eruption that I'll mention is the large igneous province. Now, you see the red area there, that's all from one eruption. And that's the Deccan Traps in India. Now, you'll also notice that there's a very long lava flow shown there, longest in the world, 1,500 kilometres long. Now, these types of eruptions have never occurred in historical times. If they did, we may even be wiped out. The Deccan Traps are in some cases linked to the extinction of the dinosaurs. They may have, it's probably not the final straw, but it would have weakened their livelihood. This is a photo of the Deccan Traps, and you can see flow after flow after flow and stretching off into the distance. Traps mean step mountains, and the little steps are due to the various lava flows, one on top of the other. This appears to be the last gasp of that particular hot spot. Just a little volcano in the southern Indian Ocean. So it's believed that the Deccan Traps were initially kicked off by a hot spot underneath India, and you can see a line running down there, and there's a bit of a gap, and then there's another line running down there to the volcano that's currently erupting. Now, the gap in between there, you can see it's moved east-west more or less. It's due to the mid-ocean ridge where new crust is being made. So that's why there's a gap in that situation. Now, the white sample that I've got floating in the tub up the front here probably came from one of these little islands down here, floated across to King Island. Another large igneous province is the Siberian Traps. Now you can see, once again, large piles of basaltic lava stretching off into the distance. Now, these appear to have been responsible for the extinction event between the Permian and Triassic, about 251 million years ago. 90% of life on Earth was wiped out at that point. due to the eruption of these Siberian traps. Now, to give you an idea of how extensive they are, this is a map. We're not quite sure how far up there it goes, but you notice that there's 72 degrees north and 56 here. So very extensive north-south and same east-west. Huge area. So you can imagine the amount of gas, a lot of it being poisonous, up in the atmosphere, would have been up there for probably years. Killed off everything. Now this one is in South Africa, another large igneous province. Now this is of interest to us here because the dolerites in Tasmania are related to the basalts that are in this area here in the Great Karoo in South Africa. And once again, it's believed these were initiated by a hotspot and dated around about 180 million years ago. And this initiated the breakup of the supercontinent Gondwana. That's a photograph of the part of it. In some ways that looks a bit similar to some parts of the Great Western Tiers here in Tasmania. But this is basalt, whereas we've got dolerite. And the difference being the dolerite is not extrusive, it's formed below the surface, whereas the basalt comes out on the surface. So where volcanic activity occurs, this is a little summary. New material is formed at the spreading centres along mid-ocean ridges. And then above subduction zones we get quite often explosive type eruptions. And then where continental crust is being stretched, we get rifting zones. And then hot spots, which can be on continents or oceanic, we get volcanic activity again. Now these last two are important in Tasmania. They're the types of volcanic activity that we've had. Now this is a black smoker which occurs close to the spreading centres in the mid-ocean ridges. What happens is that seawater is sucked down into the crust, which at this point is hot. Because it's a hot, salty water, it absorbs minerals, and the hot water then rises, comes to the surface, hits the cold seawater, and the minerals precipitate. And that's why you've got this black smoke. That's the minerals coming out in the water. And these then drop, often forming a mound, which can be eventually formed into an economic deposit. Rosebery mine has been formed in this way. So you've got lead and zinc being brought out of the crust and precipitated in a much more concentrated form so that we can mine it easily. This is a possible explanation for a hotspot activity. We're not really sure how they operate or why they operate for so long. But in the mantle, we've got hot material, rises, cools near the surface and goes back down again, so it's just like a bubbling pot. And where the hot material comes to the surface, we can often get a volcano. Now hotspots generally form volcanoes at weak spots in the crust. So going back to that Cosgrove hotspot, we'll have a look at it a little bit later again, but often there are long gaps where there is no volcanic activity, And that's been related to the thickness of the crust. Where it's thick, don't get volcanoes. Where it's thin or you're getting faulting, that's where we get volcanoes. Now the style of the volcanic eruption is influenced by a number of factors. I've just put down 4 here to keep it fairly simple. But the viscosity of the magma, if you've got a viscous magma, you're going to get an explosive, gone the wrong way. You're going to get an explosive eruption like this one. If it's fluid, you get an eruption like the one on the left. The temperature of the magma will influence the type of eruption. Generally, the hotter, the more explosive you get. The gas content of the magma, if you've got a lot of gas in it, you're going to get an explosive type of eruption. And the crystal content of the magma, the more crystals in it, the more explosive it will be. So the one on the left is in Iceland, where you've got virtually a spreading centre type volcanic eruption. Generally we don't see these because they're below the sea, but in this case we can see it in Iceland. One on the right is in Bali, and that's a subduction type eruption, and these can be quite explosive. And you can see the great cloud going very high in the air there. The shape that the volcano makes is influenced by the type of material that's being erupted. So basalt can flow very easily, so you get very long lava flows and more or less a flat volcano. Andesitic lavas, which generally are in subduction areas, and they've absorbed material from the crust as the magma goes through it, so they generally have more silica. The lava is more viscous and won't flow as well. And finally, rhyolite, which has even more silica, you just get a dome built, doesn't flow. Now we can get some interesting mineralogy in volcanoes due to the fact that as the magma comes up through the crust, it can assimilate rocks that are above it. Now, the top one is a volcano that came up through sulfite material in the crust, and so you ended up with some rather unusual anhydrite, sulfate containing mineral, and something like 20 million tonnes of sulfur dioxide went into the atmosphere. And downwind, where it absorbed water and rained, get acid rain. The one on the bottom, the sediments went through a phosphorus-bearing layer and ended up with apatite in the erupted material. So we can get lots of variations due to the fact that the volcano is coming up through crusts of various types. This is a spectacular eruption in 2022 in Tonga. This is probably one of the best recorded instrumentally eruptions ever for its size. The sonic boom was heard in Alaska, so something like 11,000 kilometres away from the eruption site. There were tsunamis across the Pacific Ocean, through to Japan, through to Peru, and also the shockwave through the earth caused a tsunami in the Mediterranean Sea. Now, the reason that this eruption was so explosive is that it occurred in a fairly shallow sea. And when the molten magma reached the water, the whole of the water column was turned into steam, and it just went off bang like a pressure cooker would if you took the valve off the top. If it had been any little bit deeper water, that would have dampened the explosion. Now this is the location of the volcano. You'll notice it's just near the Tonga Trench. The Tonga Trench is where the Pacific Ocean is subducting below the Indo-Australian plate. And you can see that on this diagram here. That's the boundary of the two plates. And the movement of the plate here is the fastest moving plate on Earth. It's moving at about 150 millimetres a year. The Tonga Trench is the deepest trench in the southern hemisphere, somewhere near about 10,800 metres deep. So that was a spectacular subduction type eruption. Oops. I'm going a little bit quicker than I thought I would, but I'll just go a couple more slides and then we'll have morning tea. Just going back to this one here, I'll just mention about the volcanic clouds. There was an aircraft flying from London to Perth in about 1982. It was a British Airways aircraft flying at night. It flew into a volcanic cloud at about 37,000 feet. And immediately all four engines cut out. The captain made a call to the passengers and it went something like this: "Ladies and gentlemen, we have a small problem. All four engines have cut out. We are doing our best to sort out the problem. I hope you're not too much distressed." The crew tried hard to get the engines running. The captain, because of the emergency situation, the engines cut out, they couldn't have pressurisation, so all the emergency oxygen masks came down, but the captains didn't work properly. So he had to increase the rate of descent to get down low enough so he didn't pass out. And 747s are not a particularly good glider. So the crew decided they'd probably have to ditch, and so they were starting to plan on ditching this aeroplane. No one had ever ditched a 747 before, so you can imagine that was a bit of a stress. Eventually they got one engine running at about 13,000 feet, and that allowed them to almost fly level. Then they got a second one going, and that allowed them to climb a little bit. But the problem was the nearest airport was Jakarta, and by that stage they were below the mountains, and there were mountains they had to climb over to get to Jakarta. Eventually they got all four engines running and were able to climb high enough to get above the mountains. But the Mayday call that they'd put out, Jakarta understood it that they'd only lost one engine. They'd lost engine number 4. In fact, they'd lost all 4. So they were cleared to come into Jakarta. One of the engines failed again, so they were down to 3 engines. Some of their electronic equipment had failed, so when they came to make a landing, they had no instrument landing system. They couldn't see out the windscreen because it was blasted from the volcanic ash, and their landing lights were inoperative because they'd also been sandblasted and weren't showing any light. So virtually they came in to land, not being of their glide path, but they landed successfully. And when they got out of the aircraft, the flight engineer kissed the ground. And his captain said to him, "What do you do that for?" And he said, "Oh, the Pope always does that when he lands." And the captain replied, "Well, don't forget he flies Alitalia." So, yeah, volcanoes can really cause problems, and in the next part of the talk, I'll just concentrate on some of the volcanic eruptions around us here near Wynyard. So we'll have a break for morning tea. Right. But,
yeah, Alan, just the photo for the Tonga volcano, was that a satellite photo or how was that one taken?
that was a satellite photo. This particular volcano was... the cloud went up 57 kilometres into the atmosphere, and it was observed using satellites, aircraft, and instruments on the ground as well, all over the world. The shock wave went round and round the world a number of times. It was just so big.
So that circular over wind, is that a blast wave? That circular, that perimeter, is that a shock wave chucking up dust or water or what?
Water and steam.
Right.
It's in the mid-ocean, so that's yeah. The cloud itself would have had some crystalline material in it, but yeah.
And what's the radial, the spokes? What are they?
I don't know. No, I can't tell you that.
Because the whole thing's underwater, is it?
Yeah, the whole thing's underwater.
Right. Okay. Fascinating.
That was worse than Krakatoa?
Yes. Yeah, bigger explosion. But probably less loss, like there wasn't any loss of life with this one, whereas Krakatoa there was. We're coming a little bit closer to home now, and this is Misery Knob. You may not have been familiar with the name of this, but this is fairly close to Wynyard, just south of. I was involved with a landslide risk assessment on this particular hill, and I wasn't really aware of it when I started, but this turns out to be a volcanic vent. Now the reason I can be sure of that is that the core that I took out and then split open had volcanic textures. You could see little volcanic bombs with glassy rims, even though they were no longer rock, this was soil. You could tell that it had been due to a volcanic eruption. And the features on the side of the hill looked very much like ancient landslides. In actual fact, they turned out to be due to the volcanic eruptions and the flows of ash that had formed down the sides. And the fact that those features were still there after millions of years meant that that soil hadn't really moved. So this Misery Knob, the volcanic centre close to Wynyard. I'll be right. Should be right. If we look at a map, you guys can see, this is a geological map of Wynyard area. Misery Knob, it wasn't marked as a volcanic centre on the map. Now, this feature here has been put on to Mount Hicks, Busby's Hill and Woody Hill. They were recognised as volcanic centres. Now, there are about 250 recognised volcanic centres in Tasmania. I suspect that there are many more that haven't been defined. Probably if we went down to the vast areas of basalt south of Wynyard, there would be many that are actually hidden underneath that area. There are about 10 that are close to Wynyard, and we'll have a look at a few of them. Now, the yellow areas are basalt. These areas here that are sort of hatched are basalt areas where landslides have occurred. The blue areas are the tillites and parts of the glacial deposits that Wynyard's famous for. The brown areas are later sediments. But you'll notice that these form lines, and that's the road up to Mount Hicks, goes up the ridge. The tops of the ridges are basalt, and when you look at a larger scale, these volcanic centres tend to be aligned north and south. This is a magnetic image of the same area, and the dark areas here are more magnetic than the lighter areas, and you'll notice that they tend to form lines more or less north-south. Doctor's Rocks here and Mount Hicks. Now, the reason that we tend to get these north-south lines is the fact that Tasmania got stretched when the Tasman Sea opened, and so we tended to get partial rifting. Not complete rifting, so that we formed seaways, but just enough to allow volcanic activity in those fissures, if you like. This is Busby's Hill, one of the ones we saw on the map before. Once again, it's a recognised volcanic vent. Sweetman's Hill in Yolla. It is not marked on the map as a volcanic centre, but if you look at this view here, you can just see the top of a transmission tower, or telecommunications tower. This is looking from Yolla, looking south. This is the same hill looking from the southwest of the hill to the top of the hill. Now, I was involved in a geotechnical investigation for the foundations of that tower, and when we drilled into the top of the mountain, we went into basaltic rock, less than half a metre below the surface, good solid rock. So that tower was able to be bolted straight to the rock, no need for any concrete foundations. And I went back to check the drill holes before they put the tower in place. So I've got no doubt that that is a volcanic event as well. This is Mount Myrtle near Yolla. Now, if you look closely, you'll see some basalt outcrops. Once again, that's a recognised volcanic vent, fairly close to Wynyard. Now, as well as the partial rifting of Tasmania, geochemists have recognised the signatures of hotspots with these volcanoes. Now, none of them have been specifically dated, but there's a range of dates that have been determined from other sites around the district. So these volcanoes happened somewhere between 70 million years ago and about 8 million years ago. But I can't give you exact figures for individual ones. Mount Hicks, another one that you're probably familiar with. It's also a recognised volcanic centre. Now this is an eruption in Iceland. You'll notice that there's a flow of magma coming away from the vent. The vent is just a little fiery fountain. Very fluid magma. This is the type of eruption that would have occurred around Wynyard in that time period. This is only probably 20 metres across. So it's there would have been a series of these in lines along the rifts, and they've formed the ridges that we can see to the south of Wynyard. Now this is the new cutting through the Doctor's Rocks where the Bass Highway now runs, and you can see, whoops, hit the wrong button. You can see a line across there. That's the boundary between lava flows. Now this wouldn't have been just one event. It probably happened over hundreds to even thousands of years, a series of flows. And there would have been partial weathering of the top of this flow before this one came over and covered it. Also, when a new flow occurs, it pushes ahead of it a lot of rubble that's on the ground, and that accumulates in this region here. Now, water can flow through those rubble layers, and so often we get springs associated with basalts due to that porous layer. The vertical features you see here are the drill holes that were used for the blasting of the rock. Now if we move a little bit further along the cutting, you can see lines running up through the rock. These are what we call columnar features. As the rock cools from its liquid state, it shrinks, and so you get these columns that form. And you'll notice that the ones here are more or less vertical, but if we go over here, you'll see they're starting to curve. Now, cooling occurs in one direction. If, in this case, the roof of the flow was probably up here, and so the cooling was in that direction, so those columns follow that direction. But when you get near the edge of the flow, you get different directions of cooling, and so these columns follow a different path. Now another example of columnar structure, this is near Columnar Court in Burnie, near Burnie Point, and you can see much larger columns, and that's due to the fact that the rock has cooled at a slower rate. Now Joe brought to my attention at one stage near Doctor's Rocks there are different sizes of columns on the foreshore, and the larger columns due to slower cooling and the smaller ones faster cooling, just depended on which, probably the thickness of the flow or whether there was hot material underneath when the next flow came through. And on the right hand side you can see the curved columns closer to the edge of the flow. Now once again, we can't be specific on the age of this flow because it hasn't been directly dated, but it's somewhere in this range. Now this is Woody Hill, a bit to the east of Wynyard. Those of you that went on Carl Jackman's excursion would have been introduced to this hill as a volcanic vent. And on the beach there are lava flows that have come from that particular volcano. And one of the interesting features of this lava flow is the fact that it has some textures underneath that indicate that the flow went into wet sediment. And when you get hot material in wet sediment, the steam generates more or less bubbles in the rock. So on the underside of that, I haven't got a photo of it, but there are some interesting features on the undersides of these rocks. And that's another view of Woody Hill. Now, after the eruptions, we tend to get this black rock, and that would have covered large areas south from Wynyard for probably thousands, if not longer, years until it weathered. And so it would have been a pretty harsh sort of landscape at that time after, say, 8 million years. But now we've got rich red soil. The basalt soil weathers fairly rapidly, and so we've got in places thicknesses of up to 10 metres of this rich red soil, and it's been a real benefit to the Wynyard district. Now these are some details of Table Cape. It's been accurately dated, 13.3 million years old, using the potassium argon dating method. Fossil Bluff has a cap of basalt, same age. Now Table Cape, it's got chromium dioxide, and it's also got lower crustal xenoliths. So it's given us some rather interesting information about the magma or the mantle beneath Table Cape, and it's unique in having these crustal xenoliths, unique in northwest Tasmania. The nut doesn't have them, but it does have the chromium dioxide. Now most of Tasmania has got a crustal thickness somewhere between 31 and 32. Table Cape, 36. And in a moment or two I'll try and give a possible explanation for that. Now this is a map of the northwest of Tasmania, geological map. Table Cape is here. Now you'll notice that there's a feature called the metamorphic complex running through here, and it's this grey material through here. That was once a seaway, and I'll show you a cartoon in a moment or two which explains how that got there. But the interesting thing is that the grey rock here, which is known as the Table Cape group, and the slightly brownish rock here, which was once known as the Burney group, now known as the Una formation. Both those rocks have identical zircon populations, which indicates that they both came from the same source. Did they both become deposited at the same time? We're not sure. Or did this rock erode from that one? Research is going on at the moment to determine that. Yeah, Rocky Cape group. What did I say? No, that's the Rocky Cape group, sorry if I said it wrong. Now notice these red features in the Rocky Cape group. That is known as the Taiatea dyke swarm, and I'll show you some photos of that in a moment. People who've been on Joe's excursion to Sisters Beach would have seen one of those in Sisters Beach. So those of you that are going to go on that excursion, something to look forward to. And there are also similar dykes in this group here. Now they have similar ages, so it occurs as one event. Now the arthrometamorphic complex opened up as a seaway of basalt due to seafloor splitting, and then it closed up again so that it's now its widest point about 30 kilometres across. And as it closed up, it basically has a weakness in the crust there. So when a hotspot has come through, Table Cape has formed because the hotspot found a weakness in the crust and came up through that point there. Now, why does Table Cape have a flat top? Question? Valentine's Peak is over in here somewhere. It's actually an Ordovician feature, much later. It formed after the metamorphic complex formed, and it's formed of a conglomerate, basically. Looks like a volcano. It's been called looks like a volcano, but it's not. Notice the flat top on Table Cape. The sides of Table Cape were probably once covered with an ash layer that went out at a lower angle. If you look at the western side of the nut, you can see parts of the ash layer that surrounded it, but most of it's gone from Table Cape. And so what we're looking at here is just the core of the volcano, the magma chamber, if you like. And the flat top is due to the fact that it probably was a lava lake. And this is a modern lava lake. They're fairly rare, but it has a flat surface. And eruptions occur, the liquid type magma just bubbles over the surface and runs down as like streams rather than erupting as like we saw with some of the more explosive eruptions. Oops. This is another one. This is in Ethiopia. And you can see the flat top, and there's not much of a crater because it just bubbles over the surface and runs down the side. Now, I'm going to look at some more subtle evidences of earlier volcanism. This is at Sulphur Creek. This is a dyke that's age is around about 700 million years. And nearby there are pillow basalts that are much the same age. Now, pillow basalts is where a stream of lava is erupted into water and it suddenly freezes, so you get lumps that look like pillows. Imagine if you were squeezing toothpaste out of a tube and just squeezed it in little jerks. That's the sort of situation you get. So this here was potentially a feeder system to the nearby basalts at around 700 million years ago. Now, I mentioned the fact that the Wynyard Formation and the Rocky Cape group have the same zircon population, so they've either come from the same source or one's been eroded from the other, we don't really know. 700 million years is the age when the supercontinent Rodinia broke up. This is another dike, this time in Burnie or Cooey, Brickport Road, that's where it was taken. The Uno Formation, which we've talked about. Now there are dolerite dikes mapped in a number of places in Burnie, but very hard to find them because they've mostly been built over or in private property. This one's not mapped, but I picked it up in a drill hole at the Cadbury's factory just there, and this one's just beside the road. Once again, it's around that age of the 700 million years, so we can relate it to the breakup of Rodinia. Out on the foreshore at Cooey, there is metamorphosed lava flows, which have been fed by those dolerite dikes. And once this age here is the most accurate date for this particular rock, which gives an age for the Una Formation, because the Una Formation, it was obviously wet when these lavas came through, so we've got features underneath the lava flows relating to hot molten material being extruded over the top of wet sediment. Now we come to the Taiatea dikes. Now this one is at Cathedral Rocks in the Rocky Cape National Park. That's the dike material there, the greyish-greeny colour. Dates on these, this one hasn't been directly dated, but nearby Detention River, they've been dated around about the 700 million year age. This is a map of the area. The Irby siltstone is the rock that's visible, Sisters Creek, or Sisters Beach, I should say. These are mapped dikes. The one you've just seen the photo of is there. Cathedral Rocks on the point. And the Rocky Cape group is this group here. This is a direct map of the area. There are dikes at the Rocky Cape Beach, Burgess Cove, Blue Rocks Point, Cathedral Rocks, and also near the wet cave at Sisters Beach. On Sisters Beach itself, both north and south, and then Detention River, which is just off the slide to the left. There's one at Detention River, or a bit west of Detention River, that has been cut by the Boat Harbour Fault, and it's moved about 4.4 kilometres. So that's the sort of movement that's occurred since these dikes were in place 700 million years ago. Now there's no volcanic activity known associated with the Taiatea dikes, but the fact that there has been volcanic activity related to the dikes in the Una Formation, we can probably say that it's certain that volcanic activity was also associated with these Taiatea dikes. But there have been some rather dramatic tectonic movements since 700 million years ago in this area, and also a lot of erosion. So that explains why they're not available for viewing now. There's a group of dikes in South Australia called the Gardner dikes, similar age, and they've been correlated with these Taiatea dikes, and they also are associated with the breakup of Rodinia. This is a proposed paleogeography of Rodinia, Western Tasmania, this little green spot there, and you'll see South Australia is up here. Now the dikes would be in this area here, close to the Taiatea system, and probably also the Una would have been in this area here. Now it's assumed that a hotspot volcano formed underneath the continent and couldn't get out, so it broke the continent up to get out. This is a cartoon that tries to explain what happened. Rodinia as a continent, and the Rocky Cape group, this yellow group on top. During the breakup, we got thinning occurring. Eventually an ocean formed to the east, and it left this area here. A bit of stretching occurring, and that's where the arthrometamorphic complex is now. Eventually that broke right through, so you've got ocean in there where the arthrometamorphic complex now is, and in order for that to occur, there was C4 splitting type eruptions. We got a breakaway on the western side of King Island as well, and also a break between King Island and mainland Tasmania. Then these came together so that the seaway closed up, and that's where the arthrometamorphic complex is now. Now, this has fairly recently been researched. The process has been developing over quite a number of years. The reason we know that the arthrometamorphic complex was originally basalt, this is blue schist, which is a low temperature, very high pressure metamorphic rock developed from basalt. Now, examples of this have been found at Flowerdale, in the Flowerdale River, and if you walk along the track from here along the English River towards the bridge where the Bass Highway crosses English River, you'll see schist, not blue schist, but it's related to this rock, and that's remnants of the arthrometamorphic complex. This is a photomicrograph of a sample taken from blue schist. The blue mineral here is glaucophane, the white material is albite, and the brown material mica, brown mica. So the blue colouring comes from this particular mineral. Now that mineral will form due to pressures that might be arrived at about 20 kilometres deep. So the arthrometamorphic complex has formed by being pushed down at least that far, and it's now 30 kilometres wide in places. So if it's been pushed down 20 kilometres, you can sort of estimate how wide it was. Probably something like the distance between Three Hummock Island and King Island as a seaway. And that's one reason why we've got a depth of something like 36 kilometres below of crust, below Table Cape. Now I mentioned Cosgrove hotspot earlier in the talk. There's Cosgrove, and it started up at Hillsborough on the coast of Queensland. It may have even started further up, but I'm not sure of any volcanism that's known up there. And you'll notice that there are some big gaps in places, whereas the volcanoes here are closer together. Now, some experiments were done just recently, and it's been found that the crust is thicker in that area. And these are places where the crust is a little bit thinner, or alternatively, there are features in the crust which have allowed the volcanoes to come through readily. Now the question is, where's the next eruption going to occur? Now we can calculate how fast this movement is. The movement is due to Australia moving north at about 70 millimetres a year. Yeah. So we can say that the hotspot is somewhere down here at the moment. Now it's been calculated that the hotspot is sitting somewhere between King Island and the mainland of Tasmania. In 2002, there were seismic rumblings in that area, which could be due to movement of the magma chamber in that hotspot. Now, there's been no eruption since Cosgrove, probably due to the fact that there's been no feature that's allowed the hotspot to erupt through it. But there are features that run across here, and we come to the edge of the continent down here somewhere. So there are possibilities for an eruption due to this hotspot. Now, the volcanologists at the Geoscience Australia have stated that there's a possibility of an eruption in the next 100 years. Now, just how big that eruption would be, we don't know, and any sort of prediction about volcanoes occurring is pretty hard to make, but there's a possibility that we could end up with a volcano out there in some time in the future. Yeah. Yep. Yeah, they are. And not related to the hotspot. The question was the Doughboy Islands and the Nut are volcanic features. The question was, is it related to this hotspot? They were related to earlier hotspots because the age of the Nut is, I think, something like 15 million years. I'm a bit vague on that, but it's quite some time ago. So that the hotspot that occurred there would be well south of Tasmania now. There's also a lot of volcanic activity on the Cape Grim here, but it's not related to that hotspot. And hotspots tend to spread out a little bit too. The head of it is not necessarily in one spot. So although it's shown as a line there, the actual eruption could come over a wider area than that circle. All right, well, that comes to the conclusion of my talk, and the references I've used to come to the information. So, open for questions.
About 50 years ago, my wife and I were sitting in our old wooden house on the Busby farm at Doctor's Rocks in the evening, and suddenly the whole house went boom, boom, and it frightened the shit out of us. And I went outside in the dark quite nervously, thinking if I had a body on the roof or a smoking a meteorite in the paddock. I didn't know what it was, but apparently on the news next day it was a tremor about 20 kilometres out to sea of what was happening physically in the seabed to cause that quite large boom.
I don't recall the exact type, but it's probably just a movement on a fault, and the fact that it's under the sea probably allowed the shock wave to come through the ground, and the shock wave would have been what you actually heard.
Yeah.
You said that the Cosgrove was the last one in the line. When did that actually occur, erupt or whatever?
I can't really recall the actual date, but it was only probably 2 million years ago, something like that.
Alan, just a basic question. What's the difference between magma and lava?
Magma is generally the name given to molten rock that's below the surface. Lava is molten rock which has been erupted onto the surface. So actually the same thing, but in different places.
Oh, thanks. There is a volcano, or the remains of, west of, I think it's west of the islands on the far northwest, and it is shaped like half of a high side of a volcano with the, what do you call the hole on the inside? Caldera, is it?
Caldera?
Caldera, yeah, the caldera. Yeah. That is underwater. Do you know the name of that island? Yeah.
Caldas.
Black Pyramid, is it? Thanks. I've only ever seen a photo of it, and I just think the islands around there are wonderful to see photos of, and I've only just seen one photo of it, and I didn't know its name.
Yeah, you'll see it well if you fly over to King Island, because you'll fly over the top of it. Yeah.
Could you go back to the map showing that line that comes down to... because I'm not familiar with those geographical names, are you able to name the towns that might be near them? Because I'm just interested to know whether these places also have this basalt soil, because I'm told only 1% of Australia's got this red basalt soil. Griffith I know, but I don't know the other places.
Cosgrove's the name of the town.
Is it?
Melbourne is here.
Yeah.
You'll find basalt soils in this area here because that's where the last...
The big blue lake, is it?
Yeah.
Is that town? Yeah.
There are basalt soils in various spots along the east coast.
Right.
So, yeah, trying to put a figure on how much is there is...
I just read it somewhere in a soils book. But does that mean that these volcanoes then, the soil came down to those locations? Because you're saying these are the volcanic eruptions.
Oh, these are not the only volcanic reactions.
Oh, I see. There's more.
Yeah,
okay.
There's a lot more. Like you've got the Warrumbungles, Mount Capitar.
Yeah.
They're on other lines.
Oh, I see. So that's a single particular
line. There are other
line.
hotspot volcanoes.
Right,
This is only the volcanoes associated with that particular line that's come close to us.
Thanks for clarifying that.
Oh, it's just a comment. The Atherton tableland is largely red basaltic soil, but it's just another. There are many areas, as you say.
Yeah.
Three Hummock Island, how did that form?
I'm not really familiar with Three Hummock Island, but I think from memory it's very similar to the mainland. I'll just go back to... Yeah, no, I thought it might have been on this map, but it's not.
Just one more, long way from home, but it's pretty controversial at the moment. Greenland, how is that formed?
I've not been to Greenland, but there are features there that go right back to the Archean. So, yeah, it's... and a lot of it's covered under ice, so it's pretty hard to investigate. But
no, but round the rim of it, it's very self-productive, very self-sustainable. But it's certainly not a wasteland.
It's certainly not
a wasteland.
No, no.
When you show us pictures of geological history and all the major, like Gondwana, Pangaea, Volcanic going back a bit, they're always on a flat map. I've never ever seen a globe with those. Has somebody made a globe showing us where those features are in the whole world?
I'm not aware of a globe, but I would steer you to, if you went to SCOTES, put that in as on a search engine.
How do you spell that?
SCOTESE.
Mm-hmm.
He's a person who's done quite a lot of work in terms of paleogeography, and he's put together movable maps so you can see what's happening in time. So, yeah, it's quite interesting to look at it, but because it's paleogeography, a lot of it is supposition. Yeah. It's I mean, you can't say it's going to be exact, but it'll give you an idea of what's happening.
Yeah, that's good. So.
Alan has already given the list of references which I'm intending to send out to all of you, and if you send me that as well, Alan, as an extra email, I'll have it.
Right. Okay. Thank you.